Right, in this session we get a clearer, relatively speaking, clearer idea of what's meant by the terms that I introduced in the previous session of uncoupled and coupled representations of a composite system, so with parts, more than one part, in the context of adding angular momenta. Okay, so what are we trying to do? So let's try to find what an expression for J squared in terms of L and S. Now J squared had, from the previous session we said it had components. Let me just check. J's. Hold on. Yeah. No. Sorry. We said J had components along the Cartesian axes, x, y, and z axes, Jx, Jy, and Jz. Let's try and find an expression for J hat squared. Now, what is J? Now I've just said it has components Jx, Jy, Jz. Okay, so expand this out. So imagine J. So you'll have Jx plus Jy plus Jz, and times the same thing, and so you'll have Jx squared, Jy squared plus Jz squared. Sorry. So J hat is L hat plus S hat. Okay. So Jx will be Ls plus Lx plus Sx. Right. So Jy similarly Yy, Jz, Zz here. So to get J squared, so J squared will just be all this squared. Okay. But L, so you can, so this is Lx plus Sx, and then Ly plus Sy, and Lz plus Sz, the squared of each. Now expand those out, and you'll get this. So I ask you to do that for homework. Now this is just Lx squared plus Ly squared, hat, Lz squared, and similarly for the S. So those two terms, pretty straightforward. This might be a bit puzzling. This represents twice the dot product. So effectively it's Lx hat, Sx hat, plus Ly hat, Sy hat, plus Lz hat, Sz hat. That's all what's meant here, right? So kind of scalar product, dot product, right? Now, why the two? Because what L hat operates on and what S hat operates on are different things, so they don't influence each other, so therefore they can commute. The order of applying them, since they don't influence each other, you can commute. So you would have got an SL before. So in one case you got an LS and another SL, but they commute, so you can hence you get two of this form. Now, let's see. So these. Now you know that L squared commutes with J squared, right? So just because L squared commutes with all this, right? S squared, for the same reason, commutes with J squared, because S squared commutes with all this. And we proved earlier, well, homework, that JZ commutes with J squared. Okay? Now, this commutes with that commutes with that. These two commute, therefore, and this commutes with that, and therefore this commutes with these two also. Alright? So in other words, you now have 1, 2, 3, 4 operators that mutually commute. So you take any two of those four operators, they will all commute. Right? Now if they all commute, they mutually commute, that means all four of them have the same set of eigenfunctions. Right? We've done that sort of thing. So now this set, now I'm going to give you the first concrete example of what's meant by a coupled representation. So these four operators, that they all commute as a set of them, this set of four, said to be a coupled representation of your composite system, your multi-part system. And why coupled? Well, coupled in the sense that the J's here depend, they're coupled in the sense that the J is a function of L's and S. So these involve terms of these. So they're sort of linked in a sense. Whereas in the next square, I'll give you an example of an uncoupled representation. And then you can compare the two, and that'll help clarify what's meant by a representation. So it's a representation then is a set of mutually commuting operators on the composite system you're talking about. Okay. All right. So with this coupled representation, in other words, these four, in this case, these four mutually commuting, mutually compatible. So you can measure all of these four simultaneously, with arbitrary accuracy. They will have the same set of eigenstates. All right. Now we're talking about J and M of J. So let's label. Well, these two commute. So let's choose a labeling of the eigenstates that are in common with these two, and the eigenstates of this and this, the same eigenstates, will also be the same eigenstates of these two. But just to label the eigenstates, let's do it this way. Okay. So this is a quantum number. It'll be one of the eigenvalues for J, and Mj, that's the eigenvalue, which is one of the components of the total angular momentum along the z-axis. Okay? So Mj, before we had Ml by analogy. Alright, so this eigenfunction here now is the simultaneous eigenfunction. In other words, the eigenfunction of all four of these operators. Why? Because all four mutually, they all commute with each other. So you can take any two and they'll commute. So what would that be? 4C2. That's six ways, 6 pairs. Is that right? 4, 3, 2. 12 over 1, 2, 6. Yeah, 6. Alright. Okay. Now, so that's a coupled representation, because these operators they depend on each other to some extent. Like the J squares here depend on the L squared and the S squared. You just see it from the formula here. So in that sense, coupled. Right? Now, to contrast with that, have a look at an uncoupled representation. Now here are 4 operators, Now you know, well these are just the orbital angular momentum operators L, and the spin angular momentum operators S. Okay, so we know from previous knowledge, earlier in the course, we know that these two commute, right? And we know that these two commute. These are orbital angular momentum. This is spin angular momentum. They're sort of not connected with each other. Well, later we will connect them, but for the moment, let's assume they're independent. They don't influence each other. Let's assume. I'll contradict that later, but for the moment. Okay, so in other words, the L's here and the S's here, they don't depend on each other. There's no formula equivalent to this kind of thing, which couples the J's with the L and the S's. So here they're sort of independent, right? Uncoupled in that sense. In the sense there's nothing like this, right? So this representation in this context, meaning a set of mutually commuting operators on your composite system. Okay, so I hope you're getting a clearer idea now of what's meant by a coupled representation and an uncoupled, right? So these four they're mutually commuting, right? All four operators, and therefore there will be a set of eigenfunctions for all four of these operators, the same set of eigenfunctions. Simultaneous eigen. They all have, well, eigenstates, like eigenfunctions, eigenstates, pretty much the same thing. So let's label those eigenstates for all four operators, the same set. Let's label them this way. Okay? So these numbers here are called quantum numbers, and they are allowed eigenvalues for the corresponding operator. Okay? So in this case, little l, that would be one of the orbital angular momentum. Right? So now you could have different values here, but that would be a different state, right? So this is one of the eigenvalues of this operator, and the ML, that's an eigenvalue. That would be one of the components, allowed discrete quantized components of L along the z-axis, right? So ML, and similar story for the spin. So S, that's a particular eigenvalue of the spin angular momentum S, and ms, the component of that spin angular momentum along the z-axis, right? So labeling it this way. All right. Okay. Now, so we've got two representations, one coupled and the other uncoupled. Here's the uncoupled representation. The set of mutually commuting operators, and here